Okay, in this video I'm going to illustrate drawing a few electric fields so that we can see how that works. And we're going to remember in general that when we draw an electric field, what we're showing is the direction of the force, a positive particle, would experience if it was in the field. This doesn't tell us exactly which direction the positive charge would go because it would depend on the current velocity of the charge. So electric fields can't just change the direction of a particle instantaneously, but it does show us which way the force would push the particle or which way the particle's velocity would be changing towards as it was moving through the field. Also, a secondary thing, the closer the field lines, the stronger the force. So first we can just look at a positive test charge, something like this, and we can imagine that all of the forces would be directed radially outward from the positive charge, moving straight away if it was another positive charge. So a positive charge here, for example, would be repelled away, or here would be repelled directly away. What we can see then is since the field lines are closer near the charge than they are further away from the charge, the field would be stronger the closer we get to the charge. So that's a simple positive charge. Alternatively, we can imagine a simple negative charge, where instead of being repelled away, a positive charge would be attracted in. Regardless of its current location, the force would be directed straight towards that negative charge. So if I had a positive charge right here, I'd be saying that force is directed straight in. And once again, we see that the field lines get more dense near the negative charge, which is an indication that the closer to the negative charge you get, the stronger the field would be, or the stronger the force would be. Okay, let's do something a little more interesting than that. Let's imagine a system that has two positive charges. In the outside of this system, the prediction is very simple. The positive charge would just move away from the nearer charge having more effect on it, causing it to just go straight away. But what would happen starting, say, at this location? Well, the first thing is that this charge would be initially very repelled by this charge, but when it starts to see this charge, or as it gets closer, it's going to get repelled by both and get turned upwards and fly away that way. Similarly, if we started down, it would start being repelled by that, but as it saw the other charge, it would get repelled and get right out of that situation. Again, we can do these two. And then the charge lines in between are the same as those, they're just not quite as extreme. So the particle again starts just going straight away, and as it gets closer to that other charge has more effect and it bends it away. What's interesting about this diagram is we can see that there's a dead spot in the middle here where there's little electric force. This means that a charged particle, like a positive object sitting in this, wouldn't experience very much force. The truth is it would experience a fair amount of force from each object, but those forces would sort of be going in opposite directions. So a big component of those two forces would cancel out, and that's why we get very little electric force in there. Let's look at the same thing, but with two negative charges. Instead of going out, now the ones on the outside are simply coming straight towards that negative charge, being attracted into him. But something, say, that was coming straight down here would come straight down towards both charges when it was far away, but as it got closer, it would see this charge more and more and get drawn in. Similarly, again, once it gets close enough, it's going to pick a charge and head towards that charge. Same idea here. And interestingly, we get almost the exact same pattern with the same dead spot in the middle caused by the fact that those forces are acting in opposite directions, canceling each other out. One more thing we can look at here, why not a positive and a negative charge? So here, again, these would just repel straight away. They don't really see that other negative charge. They're too far away from it, and then they get too far away from the whole system and they fly off. These guys would just come straight in, again, not really seeing that positive charge and being able to be repelled by him. But what's interesting is these ones that start like here, where first thing it's going to want to do is just get away from that positive charge. But the further it gets away from the positive charge, the more it's just going to be attracted to that negative charge and get sucked back in. So all these guys are going to try and get away at first and then get sucked back in. And obviously the one that goes straight in between the two. And what we're getting here is a very high density of field lines in between the two things, which is reflective of a very large electric field, which would come from the fact that these two are working together to both push the positive test charge in the same direction, repelling from one side and attracting to the other. So that's how we draw electric fields. We start at the positives, we end at the negatives because positives try and get away from the other positives and they come towards the negatives. We consider which charge we're closer to when we're trying to decide which charge is going to dominate the interaction. And we look for regions with high amounts of field lines to represent large forces and areas with a lack of field lines that show where the electric field might be relatively low or where the two electric fields might be canceling each other out.